Hello, everybody. My name is Hassan, and I recently graduated and started working at the Camcom company in Gothenburg. But what I'm going to present with my former colleague Kobra, it's about some of the project that we are doing related to predictive maintenance at Halmstad University. So first, I'm gonna talk about smart distribution grids, which was basically some of the result from my PhD education. This project was a collaborative work with the local energy distribution company in Halmstad. So the data that we got is mainly coming from this company. In general, power grids can be divided into three different sectors: generation, transmission, and distribution. And the distribution part are considered as the most vulnerable sector in this power grid because of the problems such as aging of the components or irregular change in the topology of the grid. And that's why many distribution system operators are looking for ways to reduce the number and duration of electricity outages. Smart distribution grids are the new generation of power grid with lots of promises. And they are capable of, they are included with two-way communication and control, and they have lots of different sensors all over the grid. With using of this advanced feature, they can improve the reliability and power quality of the grid. By reliability, we mean that the number and duration of the outages mainly, and power quality is related to the deviation in the voltage and current waveform. The main improvement, reliability improvement with smart grids are based on real-time monitoring of the data. And these data are usually coming from high-frequency sensors. However, there are lots of other information, such as historical data and low-frequency measurements that are available but rarely used for predictive maintenance. So in general, we can categorize the available data in smart distribution grids as sensor readings, failure records, and grid information. Here, by quality of the data, I'm referring to the relation with the reliability and power quality of the grid. As I mentioned, the majority of the improvement are based on real-time monitoring of the high sampling frequency data sources. But what I did during my PhD is using other sources of information and dealing with the limitation they have to find weak spots in distribution grids. And by weak spots, I mean the components with degraded reliability and the areas in the grid with power quality problems. I divided my work in three different categories. One is fault analysis, the other one is reliability ranking, and the third one is smart meters data analysis. For fault analysis, we mainly use the historical failure databases. This database contains information of the power outages, when they happened, how long they last, where they happened, what was the cause of failure, and which component was affected. Now, if we are interested in finding the correlation between these features with failure in underground cables, we can use a different method. One of the methods that we used here is generating association rules. By association rules, we can have a rule such as digging our morning as a prior of the rule and underground cable as a posterior. One way to interpret this rule is that if we know that there is a failure happening in the morning and the cause of this failure is digging, there is a high probability that the affected component of this failure to be underground cable. We use these rules, especially the rules with two items and the conditional dependency between them, captured from association rule, to automatically generate Bayesian networks. This Bayesian network is some kind of representation of the correlation between features. And if I zoom in, for example, we can see that our morning is correlated with digging and outage duration between 2 and 3 hours and failures in power cables. If I connect more rules to this figure, we can see that mainly happen, the digging mainly happen in one of the main station, and also aging of the cables is one of the common cause to have failure in power cables. One of the interesting results we captured from a statistical analysis of this data was that underground feeder cables, especially PILC cables, are one of the most faulty components in the grid, which cause long outages. So we mainly focus in this component for lifetime modeling. One of the important characteristic of power cable is that in case of failures, the companies usually remove the faulty part, not the entire cable. So the rest of the cable is somehow as bad as before. So this repairability characteristic of power cables should be considered when we are trying to model the lifetime of these cables. So in the first step, we only consider the age of the cables and the previous failure to model the lifetime of the cables. And in the next step, we add additional factors such as length of the cables, number of joints, geographical position, whether they are high voltage or low voltage, to estimate the failure rate for every individual power cable. To consider impact of different factors, we use proportional hazard model. This model contains two main multiplicative factors. One is baseline failure rate, is estimation of the failure rate based on the age of the cable. The other part is the impact of different factors. And here we have at-risk indicator if a specific cable for a specific age is still in service or it's censored. And the regression parameter beta can be estimated by maximizing this likelihood function. From this, we can estimate the failure rate for every cables. And at the end, we rank the cable from highest failure rate to the lowest. As I mentioned, it's important to consider the reality of the power cable as a repairable component. We show that if the cables are considered as repairable or non-repairable, not only the baseline failure rates would be different, but also the impact of different factor and the significance level would be different. Consequently, they produce different ranking lists, and the differences in some cases is not negligible. To evaluate the result, we looked at recently failed cables in the grid. During the 4 months period after creating the list, we had 3 failures on high voltage power cables, and all these 3 cables were ranked on the top 15% of our ranking list. At the moment, company is using the high-ranked power cables in the list to perform some kind of field test to decide whether to change the cables or repair them. In the next part of the project, we looked into the smart meters. Smart meters are the electrical devices available at every household for mainly using at the moment for monitoring the electricity consumption. But actually, they can monitor other features such as power quality. So we modified more than 1,000 of these smart meters to be able to collect more data, especially related to power quality. And in case of power quality problems, usually these smart meters generate an alarm. So we use this information for detecting which area in the grid would have more power quality problems. The data look like this, and because the precision of the alarms are in 1 second, we consider very close the input data that the time difference is less than or equal to 1 second to join together, and we create a burst of alarm from this data. Then we looked at these bursts, and we have 3 different general situations. If they may happen just randomly together at the same time, these alarms from different smart meters, or there could be a problem in the grid that cause this alarm in all of these smart meters who are connected to that part of the grid, or it could be a customer generating the alarm and it propagated to other customers. So except the first one, the other two are important for the company to, in order to strengthen the grid and avoid power quality problems for other customers. To do the analysis, we also consider the topology of the grid, and we use hypothesis testing and saying that, okay, if the neighbor customer are happen to occur more often in the burst compared to the distance one, then we can say that the power quality can propagate in low voltage grid, and this propagation can be detected using smart meters. Here are the results from two substations, substation S and T for two cases. The red one is when the customer are neighbor customer, and the blue one is when the customers are distance customer. In here, we define the neighborhood if they are from the same branch of the grid, of the tree structure of the grid topology, or if they are not. The hypothesis test result shows that these distributions are statistically significant, different from each other, and also visually we can see the customers, the neighbor customer generate alarm in the burst more often than the non-neighbor customers. Another way to represent this kind of co-occurrence is using co-occurrence network, where here the colored circles are the smart meters, and the location is captured, and the location of these captured from GPS coordinate of the smart meters, and then the ones with the same color are coming from the same branch. The links between the smart meters corresponding the probability of the co-occurrence of the alarms in the same burst. So this kind of representation gives the company an idea of which part of the grid has more power quality problems compared to the other part of the grid. Yes?
Hello, everybody. You see my name on the screen, and I'm working in Halmstad University. My colleague introduced a little bit of our work in Halmstad. We are coming from academic background, but we are doing applications in real domain. So we are doing predictive maintenance, or even in a broader context about data-driven analytics on different domains, including smart energy, or automotive companies, and even we do it for healthcare data, like we do it for patients, predictive maintenance for patients. This year I didn't prepare slides for healthcare domain because I didn't find any people who are coming from hospital side, but next year maybe I will do that. Today I'm going to focus more on district heating, which is in the broader domain, which is called smart energy. I guess most of you are familiar with district heating, more or less. This is a nice picture of how it works, to know how it works in different places. You know that here we have the heated water in the central station, then it goes through the substations and they use it for different reasons. But to me, as a data scientist, where is data now? We hopefully have smart meters at the entrance of each substation that different signals are collected there. So hopefully I find what's interesting for me as a data scientist. I can see how much power this specific substation has consumed, what's the flow, which is correlated with power. So if you use more water in your houses, then the power consumption started to increase, and vice versa. And the supply temperature, which is the temperature of the hot water coming to your house, and the return temperature is the temperature of the cold water coming out of your house back to the station, and a lot of other interesting signals. I just mentioned them here. You see, they look like time series. Yes, they are time series. They are time-stamped data in different resolutions. Some companies gather it in every 15 minutes. Some companies collect it in every an hour. It differs, but they are time-stamped data. I try to do my presentation as simple as possible to show you that doing predictive or descriptive or prognostic maintenance is not something very complex. You can do it even very, very simple things that you can capture from your daily life even. For example, for the district heating domain. We know that time series in global have something called seasonal trends. We have it in district heating data as well. You know that, and I know that, and everybody knows that this hot water coming to every substations, which might be houses, which might be apartments, which might be your working place, your university, your company, use it for washing in global, which has a very specific term called domestic hot water consumption. And we use this hot water for space heating. We know that people don't use space heating during summer, but during winter, they use it both for the same, both for domestic hot water and space heating. So this hot water coming to the buildings used for these main two purposes. I want to show another piece of my puzzle. During summer, we know that it's domestic hot water consumption. Who affects? The inhabitants of the buildings affects the hot water consumption. But during winter, both the building characteristics and the inhabitants affect. So I have now some cues to show that which type of buildings we are working with. We have villas, we have apartments, we have public administration buildings, manufacturing companies, and shopping malls. So we have different types of buildings, and if you think you have a kind of daily routine, whether you're living in an apartment, whether you're working, you have a kind of daily routine. You wake up at a specific time, not every day at a very specific routine, but if you think you have almost similar routine between different days. I'm using all of these pieces of puzzles to put them together to show you how we find predictive maintenance interesting for this domain. So this is the annual consumption, the real data. You can see that this is the annual power consumption for a specific building during a year. I'm zooming over a specific period. It's the same data over months and the same data over a week. I'm a data scientist. I'm doing magic. And you can see here, I extract data and show you. I didn't show how I did it because I want to show that it's possible. But for that specific building that you saw, you could see different fluctuations. You see here that this is the daily power consumption pattern during winter for that specific building. So this specific building more or less use this specific pattern for their power consumption. They have a peak near 9, 10 o'clock in the morning, then it drops, then it starts having another peak near 8 in the evening. What can I use? I can use it for descriptive maintenance things like when I know what's the typical daily behavior of each building, I know that during summer, the inhabitants, so I can now know that what's your power consumption during summer, what's your behavior as an inhabitant in a specific building, and during winter, I can plus inhabitants have the building characteristics. And further, I can go to do anomaly detection. I can find unusual consumption behavior in your daily pattern. I call it unusual because it's not always a problem. Sometimes it's a problem, and sometimes it's your unusual behavior. For example, the inhabitants has changed, so they changed. And I can do also some explorative analysis. According to summer consumption, I can now see some similarities between different buildings and who affects during summer the inhabitants. So I can see which buildings have similar inhabitants during summer and which buildings have similar characteristics during winter. And I can do even more further explorations, like I have the building categories. I know which buildings are apartments, which buildings are universities, which buildings are schools. But you know, these companies doesn't have very good labels for the buildings. If I have some good label data, then for not the whole, but for example, for 200 buildings, if I can conclude that I can guess or I can estimate the type of category, then it can be estimated for the whole buildings. And I can do some clustering. For example, what are the typical daily patterns for buildings? I'm gonna show you the examples. This is again real data for a villa during, this is a kind of confidential data. I don't want to say which city and which year, but this is the specific patterns. You can definitely see that I can extract two typical behavior for that building, these two. So I can now extract what's the typical behavior for that specific building. If it change, so the alarms can then go up and show maybe there is a problem with the system, with the substation, or maybe just a new person come in. Unusual daily behavior detection. You can see here that I used data from a public administrative building. I did some extraction of their daily behavior, ended in these two. And I look at the data, and I found these 3 days totally unusual. And I take a look into the time series data. I see that, yeah, they are really different patterns. But it's not possible for an expert in the smart energy domain to look every day in a specific building. I can do that in an automatic way and then just show, and then, yeah. For the clustering, I just put this slide to remind everybody what's the meaning of clustering. Clustering is a kind of descriptive modeling. It means that you don't need any previous training. I just do the clustering, and you can see at the end that different similar buildings are going to gather together. This is a plot that shows what I did. This is the daily power consumption during winter. What does this plot mean? Each data point is representative for every substation. So I worked on 200 substations that I have their labeled categories. The colors shows here, you can see the type of buildings. I wanted to see if my assumption is true. Yeah, it worked more or less accurate. You can see that these dark blue and these green ones are more or less the same categories. They are apartments in that company. So the similar buildings are near together in their how they are using power in their daily pattern. These purple ones are, which is called public administrative buildings. So I have a cluster over here, a cluster over here, and a cluster over there, or maybe even I can add more. But you can see that most of the manufacturing and the red one are the shopping centers using power similar, but they are not similar to how people use power in their houses, in the apartments. So now what can I do with this type of data? I did it on 200 buildings and it worked. And I have 1,000 of substations without categories attached to them. So now I can rely on maybe 10 or 20 neighbors. Neighbors means neighbors of closest buildings in how they are using the power compared to my own power consumption. So I can rely, if I vote for the most closest neighbors building categories, because public authorities are more or less the same, apartments are more or less the same, and shopping malls and manufacturing companies are again the same. But you have seen some anomalies there and there. These buildings are detected as, they don't use power consumption similar to no other buildings. Then we can ask the experts to dig into why. Maybe that specific building is not good insulated, so they are using a lot of power. Maybe they're using power. For example, we dig into and we found that some of these are locker rooms. So people go and take shower at the same time. A lot of people do that, and at the same time they go home. And so the sudden drop and sudden peaks you can see, but no other buildings did that. So it has different reasons. I can do the same for summer, the previous plot for winter, and this is for summer. I did the same, and you can see. This is how inhabitants affect. The previous was both inhabitants and the building characteristics. You can see again some anomalies. And my last point is doing clustering. What clustering can help? I did clustering. You can do clustering in any of these data that I presented. I did it on different daily patterns during summer and during winter separately and try to find the similarities here. And this is my last point. I end up with 2 clusters for summer. So I did on 200, 300 buildings. Try to cluster their different patterns for winter. I did it for summer. And I want to see how these 200-300 buildings are scattered over this confusion matrix, if it's called it. It's not a confusion matrix. It's a kind of a table that shows that, for example, these are the type of buildings. I told you that these 2 are called apartments in Sweden. These are shopping malls. This is called the public authority buildings, and this is the manufacturing companies. You can see that here are more apartments, their summer consumption. Less are here, but more here are where people work. They have that pattern during summer, and they have this pattern during winter. These are more or less similar, and this is another typical behavior. So I try to summarize what we are doing in Halmstad University with different industries, but mainly today we focused on smart energy domain, but we are not limited to that. We like playing with data, with time series and these things to dig into the rabbit hole, but definitely we need experts to help us to see if this is interesting or if it's just interesting for me as a data scientist, not in a expert view. So thank you very much.
Thank you. Thank you very much.
Thank you.